Today is Tuesday, April 16, 2019. We're having a conversation with Professor Merton Flemings of MIT, who is a luminary in the field of materials science and engineering, and one of the founding fathers of the science of solidification. This interview is being conducted by and sponsored by the American Institute of Mining, Metallurgical, and Petroleum Engineers. It's part of the Oral History Project. My name is Diran Apelian. I'm a professor at WPI and honored to say one of Professor Fleming's past students and still learning from him. I want to thank you for hosting us in your home here, and we're looking forward to the conversation that we're going to have. Thank you.
Thank you for being here.
Professor Flemings, it would be very useful for you to share with us your early years, your childhood, schooling, your interest in engineering.
Well, I led a pretty normal New England childhood, descendant of farmers and merchants in New England for some years. Grew up in Worcester, Massachusetts, right around the corner from Worcester Polytechnic Institute, incidentally. Had a wonderful physics teacher and a grand but difficult math teacher. Was interested in things, making things work from the time I was very young. My father was quite set on Worcester Polytechnic Institute for perfectly normal family financial reasons. I thought WPI was a wonderful school with only one disadvantage, was that I lived around the corner from it. And when I was admitted to MIT, I took that as a wonderful second choice for my father and first choice for me, and that was the beginning.
As a young man growing up in Worcester, were you a tinkerer? Were you building things, making things? Tell us about those years.
I was a tinkerer in a sense, with a little workshop down in the cellar, and always interested in building things I could use. But I wouldn't say I was like some of the young people today who kind of do the most amazing things when they're young. I was also interested in the outdoors and spent a lot of time that way as well.
Can you share with us some of the influences that took you towards the path of engineering, technology, science? Were there high school teachers who influenced you? How did that come about?
They were maybe even primarily the high school teachers, the physics teacher especially. But beyond that, I was looking for, really at that early age, I was looking for a kind of profession that I felt I could make a difference in. I had a second choice, and that was journalism. I had an uncle who was a journalist, actually happened to have been killed in the Second World War. And I was interested in literature, and I thought that would be a wonderful career. But then I thought, with the strong help, I must say, of my grandfather, I felt I could make more of an impact in the field of engineering, and I chose that route.
When you matriculated at MIT, at your university, to start your university journey, how did you choose metallurgy materials? You had so many choices: civil engineering, chemical engineering, so many choices.
MIT, I suppose like most engineering schools today, admits people broadly in any field. And certainly in our case, we were expected then to make up our mind by the beginning of the second term, or at least by the middle of the second term of the first year. And I dallied a little with thinking about physics and decided that's where the competition was pretty stiff. And maybe it was further removed from hands-on things that I was interested in. Mechanical engineering was a choice. But in the end, the decision came down, I think, more than anything else, to the fact that I had two mature fraternity brothers, both of whom were in metallurgy, and they told me it was a wonderful place to be. And I said, that's good enough for me, and I chose metallurgy.
In those years when you were at MIT, they were the post-war years. I think you started at MIT in 1947. Tell us about that era, right after World War II.
They were wonderful years. They were the beginning of years of enormous change at MIT. On the student side, my freshman class was about half people like me right out of college, right out of high school, and the other half veterans who were there on the GI Bill. So it was a most unusual and certainly an exciting 4 years for that reason alone, as well as for many other reasons. Then, secondly, the MIT in general and the Department of Metallurgy then in particular had been major players in the technology of the Second World War, both in terms of radar, especially in terms of the atom bomb, and in other areas as well. Our department head, for example, was the associate head of metallurgy at Los Alamos during the Second World War. And they came back with a new vision after all the interaction they'd had with scientists at Los Alamos and the other laboratories. They came back with a new vision of what metallurgy could be and where it could go. And changes then were beginning on the academic side. But in the meanwhile, the department was largely old-style metallurgists, many of whom didn't have doctorates, but had immense industrial experience, close contacts with industry, and they too had something to offer. And there we were as undergraduates, a part of this change that I think was wonderful for us, and certainly helped us, I think, have the courage in later years to continue these kinds of changes in the field as we perceived it and as we practiced it at MIT.
You're describing a very special era where you had the best of both worlds. You had a great deal of industrial experience that was your mentors. At the same time, you had
the beginnings
of scientists who were coming back from Los Alamos. So you had the mix of the best of both worlds. And do you think that continued on at MIT, or it shifted over time?
We had the mix of two great worlds. And it was a characteristic that has continued at MIT during all of the years since then. And sometimes we compare it with a pendulum swinging back and forth. I'm not sure that's a wholly accurate analogy, but if you think about it as a pendulum, it is true that in some years following the beginning of the 1960s, engineering science became increasingly strong. And by the way, I was totally supportive of it. Moving the department, helping the department move toward incorporating more science in the curriculum, more science, more engineering science in the curriculum and in the research. At the same time, by the late 1970s, it seemed to me that we'd maybe gone a little too far, that we'd forgotten how important the hands-on activities are. Some of the faculty, not me, I am proud to say, but some of the faculty had largely lost touch with industry and industry needs. And at that time, I and a number of other faculty members felt strongly it was time to bring back more of the hands-on activity, more of the interactions with industry, and I certainly undertook some actions at that time to help that happen.
In your early years at MIT, can you tell us about some of the professors who influenced you?
Well, in my early years at MIT, I would say there were two faculty members that stood out. One was Nick Grant, and by the way, both of these were strong members of the metallurgy professional societies and professional community. Nick Grant was my undergraduate advisor, a former football player from Carnegie Tech, who was interested in a whole lot of things in the world beside metallurgy, but who was a very accomplished and successful metallurgist. Howard Taylor was a man brought in after the war, hadn't been there before, but who had practical foundry experience at the Naval Research Laboratory, and really in the 50s built a wonderful foundry laboratory at MIT.
In addition to professors at MIT, I'm certain that there were classmates and peers in your class that also were influential in your early years. Could you talk about that?
Well, I had two sets of classmates that were influential. The veterans that came back opened up a whole new world, maybe a little sooner than was healthy for an 18-year-old. But I think, having said that, I think it was very healthy, and indeed they brought a perspective both of hard work and of a little bit of hard playing now and then as well. In the later undergraduate years, and particularly in the graduate years, I had two roommates from our department, David Rigoni and Ed Huckey. We studied together as undergraduates. In graduate students, we lived together. We did our theses together, and I can remember many long nights in the laboratory using equipment that was only available to us in the evening, and having the companionship and I might say the competitiveness of two fellow graduate students was a very healthy thing for me in maintaining my equilibrium going through those also exciting years.
Did you keep up with them after graduation?
I certainly did. One of them lives very close now in New England, and one in California. But we both chose the academic career. Dave and Ed went directly into the academia. I went to industry for 2 years and never regretted that, but was very happy to then join MIT after that time, and have been there ever since.
While you were at MIT, undergraduate and graduate years, did you have any internships with industry, or did you have a lot of contact with the industrial world?
In our undergraduate years, we did take a tour of industry. We toured industry that doesn't exist today, at least where it was. We had a wonderful tour of the brass industry in several different companies in Connecticut. Visited a jewelry making company, which in fact I guess does exist today. We visited a steel mill, which is a totally different operation than it was then. I worked one summer, the summer after my junior year. I worked in a heat treating outfit for the first half of the summer, and I had an 11-hour shift, and there was some interest in it. But then a job in the second half of the summer came through to work in a laboratory of a naval laboratory down in Rhode Island. And I thought, well, I owed it to my field to go work in a laboratory. And so I left the 11 o'clock job in a sweatshop to go to the laboratory. And I mean no offense to government laboratories in general, but this laboratory at the end of the Second World War didn't quite know what to do, and they didn't know quite what to do with me. And I was sufficiently bored in the work that I decided I'd rather be out in industry than working in a pure laboratory. Those are my last 2 summers. The first 2 summers were totally unrelated to profession, but have remained with me as 2 of the best summers in my life. Following my freshman year and my sophomore year, I was I guess you'd say, lumberjack for the first half of the summer, working for the Forest Service in Idaho. For the second half of every summer, the fires came, and our job was fighting fires. And those wonderful summer days will, as I say, will remain with me as long as I'm around.
Mr. Flemings, once you graduated from MIT, you had choices to make to go into academia, laboratories, or industry, and you chose industry. How did that come about?
Well, you've mentioned my 2 fellow graduate students, Dave and Ed. We had spent our graduate career competing with each other to see how quickly we could graduate and still do a competent job. And we all 3 of us finished our degrees in a time that is rather shorter than the average of those days, and certainly of these days when the time seemed to be somewhat longer. And at the end of that, much as I had found it thrilling in a sense, I thought it was time to leave the university and go and see what the other half of the world is like. And I went to a foundry laboratory in New Jersey and spent 2 very good years there.
Tell us about your experience at the foundry laboratory in Mahwah, New Jersey, at the American Breakthrough Company. What was that like? What did you do?
Well, a part of my graduate work had been to, had a pretty practical objective to develop ways to make stronger aluminum castings. And we showed in that work that something that was kind of not thought about then, but part of the work showed that dendrite arm spacing was a very important factor affecting mechanical properties. And we experimented with ways to do that in the laboratory, to make simple shapes and chill them, we say, cause them to freeze rapidly, to get a fine dendrite arm spacing, but still maintain the feeding and the soundness of the casting. And my job at then called American Breakthrough Company was to take those ideas and make real castings with them, and show that these ideas could result in a much better quality aluminum castings. I mentioned the importance of dendrite arm spacing because that was the key central one. But of course, there were other parts of the recipe as well. So I spent 2 years in industry applying these ideas. We had a number of customers by the time I'd finished for at least pilot scale operations. That is, we were actually producing castings with guaranteed properties significantly higher than those then available. Well, after 2 years, I felt my job there was done. But those ideas and those applications had resulted a few years later in the development of military specifications and later society specifications for the so-called premium quality castings that are now made today again.
You mentioned your two classmates and your close friends at MIT years, Ed Huckey and Dave Rigoni. What happened to them? Where did they end up?
Well, Dave went on to become eventually the president of Case Western Reserve University and later a venture capitalist before retirement. Ed Huckey became a very successful faculty member and retired a good deal younger than I did to play tennis in California.
Did they have any influence on you for you to leave industry and to return back to MIT and join academia?
Well, I couldn't say no, maybe a little bit. But I tell you, industry was far better than the naval laboratory that I had worked in some years earlier. But I was still aghast when at 5 o'clock every day, the workmen all laid down their tools and went home, and there I was with my day's work, in my view, not done. In other words, the pace at that level, at least, of industry that I encountered at that time was lower than I was anxious to have, and so I used toward the end of my second year at the foundry, I used my vacation to go and visit schools and apply for jobs, which is another story of another time, if I can go on and tell you. This was now in what would have been 1954, I guess. And it was a time of huge expansion still of the university systems and engineering in particular in the United States, so that schools were hiring faculty in ways that hasn't happened since, and certainly is not happening now. So when I went and I made a kind of grand round circle trip in my car visiting universities, starting clockwise at Penn State University, and I may not get these all right, but then out to Iowa and up to Michigan, and then Cornell, and then MIT. And something that couldn't happen today, but some of the universities indicated strong interest. One of the universities offered me a few weeks later an associate professor, that is passing one of the first step, an associate professor in charge of their foundry. But then I came back to MIT and told my thesis mentor, Howard Taylor, that I was ready to go back to the university, and I thought that as it looked now, I would take that position. And he said, "Oh," but then he said, "You know, we have quite a lot of research operation here, and it's pretty exciting. And I'm not the department head, so I can't talk about a faculty position, but wouldn't you like to come back and be a research staff member?" And with what should I say, with some embarrassment, I said, "Thank you, but no thank you. I think now I'd like to take a faculty position." And he said, "Well, okay, I'll work on it." And he worked on it, and pretty soon I was offered a chance to come back to MIT, and of course took the opportunity.
Mr. Flemings, can you share with us your early years at MIT as an assistant professor, and then being promoted to associate, then full professor? Tell us about that journey, because it was also a time of many, many changes in American cultural life as well, and political life. So tell us about the early years.
Well, I came back to MIT happily, as I've said, and continued my research in the fairly applied aspects of foundry practice. Now under the direction of, or at least in association with, the senior professor Howard Taylor. We worked on gating and risering and fluidity. We tried to treat these subjects quantitatively, and did so where we could, but they still were subjects quite narrowly focused on problems of the existing foundry as it stood. I was also wonderfully engaged in teaching broad metallurgy subjects, and all of this was at the time when MIT was now moving more quickly away from focus on specific industries and more broadly onto questions of engineering science. The aim of the Dean of Engineering, speaking at that time, was that we would work on subjects and work in ways that would be broadly applicable to many industries, not just to one industry specifically. As a result, not too many years after I returned to MIT, it became clear that there was not going to be a place much longer at MIT for the large machine shop that we had, or the metalworking shop, or the enormous electric generators that were in existence in the electrical engineering department, or the foundry. And it was also clear that if I was to stay at MIT and get tenure, if I was to have a full career there, I would need to change also, which I want to say I did with alacrity. I did with excitement. I thought it was the right way to go, and I thought I could do it. Already at this time, the senior foundry professor Howard Taylor was ill and soon passed away, and the burden was then on my shoulders to do or not do what I should do with regard to the foundry. So, in short order, we shut the foundry down in the sense that we decreased the laboratory staff population from some 6 non-professional people to 1. And I began to look for new areas of research, that is, areas of research where I could use my expertise and my students' expertise and contribute, I felt, in important ways to the foundry still in the future, and maybe to other areas such as the steelmaking industry. My aim was to find areas where we could continue to contribute to industry, but in a more general and deeper way. From that point on, I sought different kinds of research support, and I used current research support in ways that were acceptable to my sponsors to undertake these new studies. all of which revolved around the study more broadly of solidification, of what went on, of understanding details of the process that were not then well understood, but always with the intention, ultimately, to use these studies to come up with useful ideas, with useful understandings, with understandings of the process that would benefit industry.
Professor Flemings, as one looks at the field of materials science, engineering, solidification processing, your contributions are viewed as being the foundations, the scientific foundations of liquid going to solid solidification processes. But the context that you've had with the industrial experience certainly set the stage and the motivation to bring in the science into it. While you were at MIT, there were also luminaries at Harvard University like Bruce Chalmers and others around the country at Stanford University, Tiller and others. Tell us about the interactions that you've had with those other key people in the field, and if they shaped your thinking in any way as well.
I had wonderful interactions with Bruce Chalmers. We had a period of a year or more where our research groups met together at least once a month, maybe more often, I don't remember, and where we shared our thinking. Bill Tiller, to pick a name, came at the field from a totally different way than I did.
Professor Flemings, do you think your industrial experience that you had at American Breakthrough and all the work you did with various laboratories helped you make the transition from foundry technology to engineering science?
My industrial experience was an enormous help in making the transition to a meaningful form of engineering science. Just to pick one example, I understood the importance of dendrite arm spacing in a practical sense. I understood it from looking in the microscope, and I understood it from the thermocouple measurements, and I had a feeling for how metals solidify. I also had a feeling for what was important from an industrial standpoint. I learned, for example, how important dendrite arm spacing was, but I also knew how important porosity was and inclusions were. I could see many fundamental problems, many engineering science problems associated with every aspect of this that would have applications beyond just aluminum casting. And I think, if I may say, there was something in me that wanted to think more deeply about each one of these problems, more deeply than one could do in industry. So, returning to MIT, I made it a point to continue to have contact with industry. And I continued to find industrial contacts over the years vital in helping determine the directions of my research. To pick a simple example, to pick just one really clear example, a few years later, after my return to MIT, by that time in my solidification, by that time in my consulting activities, I was working with a number of steel companies, as well as a few foundries on solidification problems, having by that time become known in the field from publications on the dendrite formation and on microsegregation. And at that time, U.S. Steel was building their first large slab continuous caster outside of Chicago, and finding a problem with centerline segregation. And the centerline segregation occurred right at the time that bulging was in the casting. You can picture it in an exaggerated way that the continuous castings were coming out this way, and with each bulge there was an area of macro segregation there, of centerline increased segregation. Well, I was familiar with hot tearing from my foundry practice, and I knew that if you pull a semi-solid metal apart, the liquid flows in, and I thought, that's got to be the answer. U.S. Steel was happy with the answer, and I think it helped them get rid of the bulging. But more importantly, they then funded me for some years to continue work related to macro segregation. And we proceeded to follow a path to try to understand it. We tried to duplicate the bulging. The experiment in which we tried to duplicate the bulging, which I won't go into the details of, showed that bulging might be there, but it wasn't the biggest. It wasn't the most important thing. To put the discovery, you might say, in different terms, the classic explanation for centerline segregation was always that the dendrites push the carbon and other impurities toward the center, and that's why they end up there. And whether you look in the older textbooks or in the steel-making handbooks, you find that explanation. The explanation is dead wrong. And we spent the next few years, one part of our research was continuing to look deeply at this problem, understand it mathematically, and develop the foundation that is now widely used in practice in solidification of all kinds of ingots, ferrous and non-ferrous.
I, for one, and many others, are the beneficiary of that wonderful book, Solidification Processing. Professor Flemings, your book has had a tremendous impact in the field, but as one looks at it, it's not structured the way most books are, where they start with nucleation theory and go on, but rather you start directly with heat flow and industrial experience. Tell us about how you put that together, which I'm sure mimics or is very similar to the way you taught the course as well. But give us your thoughts as to how you put that together.
Well, that's right. The book is based on a course that I taught, and in both the course and in the book, I tried to deal first with the general overarching problems in casting and the overall different processes, ranging from single crystal growth through the sand castings, and tried in each chapter of the book, following the general introduction, to deal with the heat and mass transfer, not of this process or that process, but of all of the processes. Tried to see where the similarities are between single crystal growing and foundry practice, and where the differences are. And mainly, I tried to keep the book mathematically simple, not clouding issues, but not delving into the minute detail, which is necessary in some instances, but not, I think, for a beginning text, or even for a text of use to engineers in industry. But what's important in practice is the basic concepts underlying equations, not how fancy the equations are. And that was my aim throughout the book.
Mr. Flemings, the Materials Processing Center at MIT is well known, and you're the founding director of that center. What were the events that led to the formation of that center?
Well, I've mentioned that by the 60s and then certainly into the 70s, I had the view that engineering science, important as it was maybe crowding out some of the other things we should have in our department. And I also felt that there was insufficient attention paid broadly at MIT and including in our department to industrial support and industrial interactions. And with these two thoughts in mind, one, developing stronger interactions with industry for our department, and more broadly for the engineering school, because this was an interdepartmental organization, both for the stronger industrial interactions and the counterbalance to some extent to engineering science. I thought a new center was called for. I went to the dean, and after considerable deliberations, the answer was, if you can fund it, go for it. And I was fortunate enough to obtain significant long-term funding for the processing center. The main initial source of funding was NASA. The aim was, and the purpose was, before we can learn to process things in space, we better learn to process them better in the United States. That funding enabled the initial start, but significant funding then came in the succeeding years from industry, and the processing center has remained in existence right up until this time, when it's now finally been joined with the Materials Science Center at MIT, and providing to that center a focus on industry and industrial interactions that they haven't had before.
Professor Flemings, you had a wonderful tenure as department head at MIT, where many wonderful things happened. Can you share with us some of the highlights from your perspective?
I'd be happy to. And to do that, I'd like to go back again, back into history. In the late 1950s, in my very early years on the faculty, the faculty was still at that point divided into quite what seemed today unusual, perhaps, discrete components. There was the two faculties who dealt only with aluminum alloys, and there were courses that dealt only with copper or with aluminum or with steel. We had a focus on mineral dressing. We had large jaw crushing machines, and I've mentioned that we had large industrial equipment. But apart from that, we didn't think of metallurgy as a cohesive field. We thought of it as an agglomeration of a lot of things, from mining to finishing. John Chipman, the department head at that time, convened a committee to reorganize the department and to reorganize the teaching. And he said, this is not the way to think about a department. And the ultimate diagram or picture that they came up with at that time was to think of it not as an agglomeration of different metals and different aspects, but with all metals at the middle of it. And that what our core was metal generally, with around the hub these different aspects. But that courses should deal, for example, he was saying even then, not just with aluminum metallurgy or steel metallurgy, but with metallurgy. And of course, things were now coming along that made that easier to think about, including, for example, X-ray crystallography. You don't do that with, you do that with all metals, not just with one. And so the teaching then moved fairly quickly to teaching physical metallurgy or mechanical metallurgy, dealing with all of the materials. Then, as the years went on from that time through the 60s and 70s, we all understood the importance of moving from only metallurgy toward materials. We thought it made sense. As the time went on and we realized that there were so many jobs for our students out in the materials industry broadly, that a lot of what we had, the understanding we had, was as applicable to polymers and ceramics as it was to metallurgy. In fact, if we were to serve our students, we needed to be moving toward materials science and engineering. And so we had, over those next decades, we had made steps along the way. But when I became department head, we had changed, and I believe had already become a different name in materials science and engineering. But we were still largely a metallurgy department. We had a small group of electronic materials people working on very small polymer aspect, small electronic materials. But we did not have courses that blanketed these different fields. We didn't have a structural course that dealt with metals and ceramics and polymers. We needed a new idea of what our department was for our teaching and for our research. And gradually, out of it, we formulated the ideas that we had to decide what we were. If we weren't a metallurgy department, what were we? And what our expertise was, what our underlying intellectual principles are, we came to believe were structure, the structure of all materials we could study and teach, the processing of all materials we could teach, the properties of all materials, and the performance, how they perform in industry, we could teach, and that those were the principles that would bring us together, and that we would need to move toward our courses in this direction, our new faculty hires in this direction, and our research, of course, in this direction. And that was my job then when I took over as department head, is that we knew what we had to do. We knew that it was important that we do it and do it quickly. And we were certainly among the first of the metallurgy departments in this country or in the world. In fact, we and one or two others were leading the movement away from just metallurgy to broaden materials. And I might say that in the beginning, it didn't wholly meet with excited approval from industry people, especially from the classical industry. But we felt we had to do it, And ultimately, I think we've had the strong support of the industry in that.
Professor Flemings, you talk about this unified vision of material science and engineering, and the transformation you made under your leadership as department head. How did that reflect in students' interests in the field of materials?
Well, first of all, the interest of the female student population of young women increased remarkably, and it was. I think that there was some hesitation on the part of young women to want to enter a department that was associated only with big blast furnaces and foundries, but had broader appeal. But the same is true of men too. Is that the move was critical to maintain and increase our male student population too, and we made the beginning of hiring women on our faculty, a trend that continued happily, strongly after I was department head.
Professor Flemings, your outreach in the community, material science and engineering community, is certainly not North America centric. It's global. Could you tell us about your experiences and relationships with around the world, not just in North America?
Well, I've greatly enjoyed my contacts with my colleagues throughout the world, and I have had many such collaborations and contacts with faculty members and with industry from both Europe and Asia. I've taken sabbaticals in these different countries. I've had students who've gone to be distinguished faculty members in both Europe and Asia. My wife is a Japanese scholar, and we had a wonderful year in Japan, where I was a visiting faculty member at the University of Tokyo, and also on a half-time appointment with Nippon Steel, and worked with the researchers in the laboratory there. The research that we've done happily has found use in an application in many countries of the world, and it's been my honor to visit those countries from time to time and see some of the applications of work that we've done. Before I leave the topic, I should say that one of the responsibilities of a department head is to accept and welcome and seek support from alumni and from industry to aid in not just our research, but in support of faculty and support of students. I did spend a fair amount of time in Japan working with companies, and gratefully received a number of faculty endowed chairs from Japan, as well as some from this country.
Professor Flemings, you're well recognized all throughout the world. You've had a global impact in many countries. Tell us about the Singapore-MIT alliance that you headed and led for many years. How did that come about?
Well, I stepped down from being department head when I was 65, after 12 years, and at that age it seemed appropriate to pass the mantle on to someone else. Of course, I was then a little bored and asked the dean what else he had in mind. And at that time, a member of the Singapore government was anxious that actually a man who had graduated from MIT, was anxious that he do everything he could to raise the quality of education, engineering education in Singapore, and wanted, at first asked MIT if MIT would start an affiliate college in Singapore. We appropriately, that is MIT appropriately, said that was not something we wanted to do, but we would establish a committee of faculty members to visit Singapore, to work with Singapore and study their engineering education and write a report and see if we could build on that in some way. So I was asked to do that, or invited to do that, and I formed a committee of comprising faculty from some 5 different engineering departments. And we worked over a period of 6 or 8 months in and out of Singapore, reviewing their education, and wrote a report. The report was greeted, I might say, with mixed emotions on the part of Singapore, because it was not, it was respectful of a strong system and bright people, but did point out areas where we felt improvements could be made. Growing out of that, then, after extensive negotiations, we established a major collaboration between MIT and Singapore, which has lasted right up to the present time, and has gradually evolved into broader activities and collaborations between the two countries.
Professor Flemings, as one looks at your work, innovation is really the common thread across all of your patents, publications, and results that have actually been commercialized and used by industry. Then after the Singapore Alliance that you led, you took on the Lemelson initiative at MIT, which is also based on innovation. Tell us about how that all came together and what you accomplished during that era.
Well, you're right that invention and innovation have always been nearest and dearest to my heart. I've always wanted to go deeply into problems, not for mathematical sophistication, but to find out what else might be down there underneath. It's so easy to find short-term solutions to problems and neglect the pay dirt that lies underneath for how you might use the ideas there in new and different applications. So I've loved to invent, and I have quite a few patents with my students over the years, 30 plus, I believe. The opportunity then arose for the engineering school to lead a program supported by the Lemelson Foundation in Invention. And by that time, in my career, I was now half-time, and taking on the Lemelson program was something that was appropriate, that didn't require a full-time faculty member, but something that certainly related to my interests. And so we took over a small program that had been formerly handled over in the Sloan School, and proceeded to expand it and develop it into a program that involved high school students from all over the country doing inventive projects. We established a number of prizes and continued a prize of $500,000 for the best inventor of the year. and basically put together a program that remains today a strong part of MIT.
The Lemelson Prize certainly celebrates invention and innovation, but on a personal level, you have had, Professor Flemings, you've had many students over the years, and invention and innovation was also inbred in all of your students, and I cannot imagine that it has not had a tremendous impact, not only to society at large, but to many other generations of students. Tell us a bit about your reflections on your interactions with your students and where they're at today and what they've done.
Well, I can tell you this. What I am most proud of in my career is my students and what they have done. And these are students all over the world. They've become faculty members, deans, college presidents. All of them have made significant engineering accomplishments, and I believe enjoy their work.
Getting emotional. So, Professor Flemings, I can surely tell you as one of your past students that that pride and love and affection is a two-way street. I know at least 20 or 30 of your past students that I'm in touch with who are with you on your 70th anniversary celebration and who are constantly thinking of you and are grateful to what you have, how you have touched their lives. So I think in a way you should be gratified to know that the good work that you've done has had a lasting effect on many of people, and it's really a circle of goodness that keeps continuing on. So it's certainly circular.
Well, I think, Diran, I think often of that 30 and the 70 and many more beside. We were, many of us at that time, in my view, were more collaborators than professor-student. Clearly there was that professor-student relationship, but my view is that we worked in the laboratory together. We tried to understand together what was going on. We were excited when we found what was going on and when we made an impact. And it's been that kind of relation that I've felt in the years since. And if anything, the shoe is now on the other foot, where I turn to some of my former students for advice and mentoring at this point.
Professor Flemings, as one looks at your accomplishments, you have so many awards. There's no way I can read them, several pages long. Highly recognized, well-deserved, from the National Academy of Engineering to other academies around the world. Surely there must be one or two of these awards that stand out in your mind. So, how do you feel about all this recognition? What matters to you? What are the ones that you covet the most?
Well, yes, I've been honored to receive the awards I have on behalf, I might say, both of myself and the students who worked with me to create the things we created. I will also say, though, that if I were to pick the kind of award, or even the award, and certainly the kind of award that means the most to me, the example I would give is the 2005 Albert Easton White Award of the ASM that recognizes both the significant accomplishments of our research group, but also the unusually, as I quote here, but also the unusually long and devoted service in teaching. In the end, that's why we're in the university, is the teaching and the students and what they're going to do. And so that's why I would pick that award as an example.
Yeah. You're referring to the Albert Easton White Distinguished Teacher Award of ASM, and that's a wonderful way of bringing that all together. Thank you. Over the years, you've garnered a lot of wisdom, and I know you're the kind of person who likes to share and to give, and generosity is in your DNA. What advice would you give to a young person, 18, 19, 20-year-older, who's getting into the field today?
I believe I would tell that person to find a job, a profession, a life work that is fulfilling, where you can make an impact, and then work at it. And besides that, find a partner to share the life with you, and plan to make an impact with him and her on the world you live in, big or small.